Metacenter. When a solid body floating in a fluid is tilted from its equilibrium position, then the stability of its equilibrium depends upon the location of its metacenter. Let us recall a solid body floats in a fluid. If the mass density of the body is less than the fluid, as in case of the wood, plastic, and ice cube, and etc., the weight of the fluid displaced by the immersed body is equal to the weight of the body, as for in case the boat, a ship, and etc.
When a body, say a ship, floats in water, it is acted upon by two forces: a vertical downward force of the gravity, which is equivalent to the weight of the body W, acting to the center of gravity G, and an upward vertical buoyancy force Fb, which is equal to the weight of the water displaced by the immersed body, which passes through the centroid of the displaced volume of water, that is, the center of buoyancy.
Now, for a floating body to be in equilibrium, the buoyancy force should be equal to the weight of the body. Also, the center of gravity and the center of buoyancy should lie on the same vertical line called the center line BG. Now, if a body undergoes an angular displacement, say in the rightward direction, then we see that the volume displaced is larger in the right side. Thus, the center of buoyancy shifts towards the right from B to B prime, and the couple is formed which tries to rotate the body.
Here, the point of intersection of the vertical line through the new center of buoyancy is B prime, and the center line BG is termed as the metacenter of the body, and the distance by which the metacenter lies above the center of gravity of floating body is known as the metacentric height, which is given by Bm minus Bg.
So this is now our problem. A plastic cube of dimension L and specific gravity of 0.82 floats in water. Is the cube stable or not? First, we locate the center of gravity, which is just in the middle of the figure, G, which would give us a dimension of 0.5 L. Then next, let's solve for the distance of the submerged part. So we will solve that through the buoyancy formula, which is the buoyant force is equal to the weight's object. For a simpler formula or equation, it would give us the unit weight of the fluid times the volume of the submerged part of the object, and it would equal to unit weight of the object times the volume of the object itself. Now the unit weight of fluid is equal to 9.81 kilonewton per meter cube times the volume submerged, or L squared, times x. X is equal to the distance of the displacement in the figure which we are looking for. Then since 0.82 is given, we'll use that to solve for the unit weight of the object. Specific gravity times the unit weight of the fluid times the volume of the object, which is equal to L cubed, and would give us a result of 0.82 L. To solve for the center of buoyancy, we will divide the x by 2. That would give us a result of 0.41 L. So our center of buoyancy is just a little bit below of the center of gravity. The next is we will solve our MB, or the height, of this our metacenter through this line, metacenter and the center of buoyancy, which would equal to MB is equal to the inertia is over volume of the displaced or the submerged. Since our figure is a cube, our formula for its inertia is bh cubed over 12 is equal to the volume displaced, which is L times 0.82 L. So this would give us this result. It would give us a result of 0.1016 L. So, to know if our figure or our object is stable, MB must be greater than our MG. So, let's solve for our MG. MG is just equal to MB minus BG. So, our BG from the figure here, so we would just, this is our BG and our MB. So we can solve our BG by simply subtracting our center of gravity to the distance of our center of the buoyancy. So that would equal to 0.5 L minus 0.41 L is equal to 0.09 L. So now, let's solve for our MG. Our MB from our previous solution is equal to 0.1016 minus 0.09 L is equal to 0.0116 L. So now, we can conclude that our MB is greater than our MG. So our figure is, or our system is stable.